everyone's technology, which is why like, I appreciate yeah, it's just like it's hard to get it all.
Okay.
All right. Well, for our final attraction of week 2, we'll have Luca finishing up his lectures and telling us a little more about black holes.
Great. So let's summarize where we left off. Is this too loud? Should I move it a bit more down? Maybe I should.
We turned up the volume in the room because of software.
Oh, okay.
We can control it there.
Okay. So last time, or the last 2 times, we started with one of the simplest examples of black holes that we know, a Reinstein-Nordstrom black hole, which is a solution of Einstein-Maxwell theory. We took the solution close to the extremality. We saw that close to the horizon of such black holes, the space-time looks like AdS2 cross S2. The size of AdS2 becomes infinitely large, at least semi-classically, as the temperature goes to 0. And because of that, we wanted to understand whether there's a parallel between these black holes and the black brains that we typically study when talking about the AdS-CFT duality. So we basically did the same thing that people did in the early days of AdS-CFT and studied the S-wave sector in AdS2, just like one would write down an effective field theory in AdS5, coming from the solution to 10D supergravity. And the action that we found ended up being very simple, actually much simpler than the theories in AdS5, and consisted of 2 terms. One term that came from evaluating the action outside of this near horizon geometry, and another set of terms, these 2, which were simply given by the JT gravity action. So JT gravity is this EFT that we've been looking for. And in principle, as I said last time, you could keep track of other massless fields that exist in the theory in this dimensional reduction, but the results that I'll be telling you will roughly be unchanged. I'll actually say what other mass looks like if you keep a scalar, what happens. Great. So we took this action and saw that the only non-trivial dynamics that are part of this action come from this boundary term. This is because the dilaton phi acts as a Lagrange multiplier for whatever is in the parenthesis, and whatever is on the parenthesis is set to 0 by this Lagrange multiplier. So we only have this boundary term that's given where we fix the value of the dilaton on the boundary and the value of the induced metric. So the only dynamics are given by this extrinsic curvature term. Now, we parameterize the extrinsic curvature in terms of the shape of a curve that's embedded in AdS2, since this equation tells us that we just need to look at a patch of AdS2. And we saw that the weights of different shapes is just captured by a relatively simple higher derivative action given by the Schwarzian derivative. The Schwarzian derivative, I forgot to write it today. I'll remind you what it was from last time. It was t triple prime minus t prime minus 3/2 t double prime over t prime squared. Good. So the effective coupling of this action, after we did a rescaling of the affine time on the boundary of AdS2, we saw that is not 1 over the value of the dilaton at the boundary, the renormalized value of the dilaton, but instead it's the ratio between the temperature of the black hole and the value of this scale and breakdown that depends on the charge of the black hole that people had found in the 90s and suggested that at this energy scale, when the black hole temperature reaches that energy scale, breakdown of thermodynamics occurs. Now, this time we're seeing that T over M breakdown appears as the coupling of this action. So the coupling of this action diagnoses how large the quantum effects of these modes are. And I just want to remind you that these T of U just parameterizes a certain fluctuation of the metric. So essentially we have some set of modes of the metric that could in principle have very large quantum fluctuations. But before we did that, we analyzed the semi-classical limit. So what happens when T over M breakdown is much larger than 1? Well, in this regime, this number is large. And in principle, if we were to do a path integral or an integral over all these shapes that are embedded in ADS2, we could now do this integral by saddle point approximation, right? So we just have to look at the saddle point of that action in this regime. And the saddle point of this action, we wrote down the equations of motion from the Euler-Lagrange equations. And one finds that the solution to the equation of motion is given by T of u equal to 10 pi u. That might seem a little bit random, but it's more clear when you look at the extrinsic curvature. The solution is just a space-time that has the extrinsic curvature at the boundary be a constant that is smoothly glued to the rest of the space-time. So this implies this. We took this solution, plugged it back into the action to obtain the on-shell action and obtain what the logarithm of the partition function, the free energy, is in the saddle point approximation. And we actually recovered the result that we quoted or we derived in the first lecture, which was the semi-classical result for a Reinster-Nordstrom black hole. But now the difference is that we have access to more. We are now able to understand what happens to these set of modes of the metric that could in principle have large quantum fluctuations. So the question now is, how do we compute the quantum corrections of this action? And let's proceed by computing the quantum corrections to one loop order. It will turn out that this action is quite special, and the result that comes out that one loop actually persists to all loop orders in variations of T. But to compute things to one loop order, what do? We just take the classical solution and expand around it. So we take T of u to be tan pi of some function f of u. Where f of u is equal to u plus epsilon of u. Or maybe let me write it as a function of tau. It's a bit more convenient. And now, in order for T to come back to itself, in order for the boundary of ADS2 to close in Euclidean signature, we have to impose that this tan is periodic. So if we look at these small fluctuations epsilon, epsilon of T should be identified with epsilon of T plus beta. So I could expand epsilon into a set of Fourier modes. That are periodic as I go around the thermal circle. And the Fourier coefficients are just parametrized by epsilon n. And because because I want T to be real, epsilon has to be real. And to this, I just have to add the Hermitian conjugate. Great. So before I proceed, let's think a little bit abstractly about the integration space over this mode. Do we really have to integrate over all epsilons, or are only a subset of these modes physical? And for that, we have to think about the isometries of ADS2 once again. So we mentioned that the isometries of ADS2 is SL2R. This is the transformation that leaves the metric invariant. So when we integrate over these modes, we need to be careful not to integrate over configurations that are related by SL2R transformations, right? Because if you do an SL2R transformation to a patch of ADS2, you won't change any of the physical properties of the patch. You will just change how the patch is embedded in Poincare coordinates, right? But for instance, the extrinsic curvature, the length of the patch, the length of the boundary of the patch, everything is invariant under this SL2R transformations because the metric itself is invariant. Great. So the integration space, after quotienting out by these SL2R transformations that can change how this patch is embedded in, let's say, the upper half plane of the upper Poincare half plane. This was Z, this was T. After we quotient out by this, the integration space turns out to be a set of functions that map circle to circles, right? Here we're trying to parametrize a function that's periodic, so it lives on a circle, and it parametrizes T of U. It maps a circle to a circle. This is what's called defense 1. But out of this integration space, we have to quotient the SL2R transformations that are the isometries of ADS2, because otherwise we would count spacetimes that are identical multiple times in the path integral, and we don't want to do that. So in general, when you have an isometry of the spacetime, you want to make sure that you quotient out that isometry from your integral over metric configurations. And if you tracked down what these SL2R transformation are in terms of these epsilons, what you would find is that the values of n corresponding to -1, 0, and 1 actually correspond to the free possible generators of SL2R. So we have to throw out these free modes, but we're still left with an integral over an infinite set of modes. Great. So we could take this expansion of epsilon of t and plug it into the Schwarzian action. I encourage you to do that in Mathematica. Plug it in here. And then expand that small epsilon n. Now, at leading order, will we find an epsilon n? Linear order, no, right? Because we've satisfied the equation of motion. By definition, the first order at which epsilon n should appear would be at quadratic order. Great. So we need to track how epsilon n appears at quadratic order. And it appears in the following way. The integral over du from 0 to 1 of the Schwarzian can be written as, so let me put the coupling here so that we keep track of it, as 4 pi squared. So we plug that configuration in. We get 2 pi squared over beta and breakdown. Beta, my bad. Thank you. 2 pi squared over beta and breakdown plus 4 pi squared over beta and breakdown times the sum over all these modes that I actually am integrating over, minus all of them but the ones from -1 to 1, of n squared times n squared minus 1, epsilon n, sorry, epsilon minus n, epsilon n, plus the Hermitian conjugate, and plus order that is cubic in epsilon. So this is just a quadratic term in the expansion. So this makes it very clear that if I look at each one of these modes, the typical fluctuation of this mode is given by the inverse scale here. So when t over m breakdown is much larger than 1, the suppressions in epsilon n will be very suppressed. It's like a Gaussian with very small standard deviation, right? Now, when this coefficient is small, then the standard deviation of the Gaussian becomes larger and larger, and the fluctuations over epsilon n also become larger and larger. So remember what this epsilon n parametrized. It parametrized the Schwarzian, which entered in the extrinsic curvature. So in the regime t over m breakdown much larger than 1, most of the configurations that dominate will have the extrinsic curvature almost constant, while in the regime T over M breakdown of order 1, all the configurations that will have an arbitrary shape will contribute to this integral. Okay? So with this in mind, let's try to compute the partition function, including the one-loop determinant of this mode. So first, before we discuss the one-loop determinant, let me make a comment about this integration space, dFS1 over SL2R. That space turns out to be a symplectic space, and it has a symplectic measure associated to it. That symplectic measure actually comes from the ultralocal measure of the metric. So we can use that symplectic measure as our integration measure for the integral over T of U. Yeah, it's I forget off the top of my head how to write it, but roughly the measure in terms of the metric can be written as dg wedge dg. With the appropriate contraction, the integral of this, with an appropriate set of index contractions. So from this measure, one can write the measure for these modes d epsilon. And it turns out that the measure over these modes d epsilon is a product over all modes 4 pi n cubed minus n d epsilon n d epsilon minus n. So you almost see the same independence that you see in the action itself over there, in the quadratic expansion of the action itself. And actually, this is a common occurrence when you consider the integral over symplectic manifolds. Great. So now, if we compute z of beta, it's given by the classical term that's obtained in the saddle point approximation, e to the s naught, 2 pi squared, beta m breakdown, minus beta m naught, times this integral over the modes d epsilon, e to the minus the action that we wrote over there, that I'll write again for convenience, 4 pi squared over beta m breakdown, sum over n squared minus 1, epsilon n, epsilon minus n. Okay, so we just have to do a Gaussian integral for each one of these modes epsilon n and epsilon minus n. And this is a simple exercise. Each one of these modes contributes a factor of beta, coming from here, beta times m breakdown, divided by a factor of n. This is a factor if I take the ratio, the determinant after integrating epsilon n and epsilon minus n. You get a factor of 1 over n squared times n squared minus 1. And multiplying this by n cubed minus n, you get an overall factor of 1 over n. So you get e to the s naught, 2 pi squared, beta m breakdown, minus beta m naught, product over all n greater than 1. I can now restrict to just to positive n, since I'm parametrizing things in terms of epsilon n and epsilon minus n separately. Beta times m breakdown over n. Good. And this product we can evaluate using a zeta function regularization. And it gives e to the s naught plus 2 pi squared over beta m breakdown minus beta m naught 1 over beta m breakdown to the power 3/2. And zeta function regularization gives an additional factor of 1 over 4 pi squared. That's not very important. So let's make a few comments about this result. So from a product over an infinite set of modes, we got this one loop determinant that depends explicitly on beta. We've used zeta function regularization. Whatever other regularization you use, it will differ by, this result can differ by a proportionality constant. The results that differ by a proportionality constant can be absorbed in S naught. Good. Similarly, we could have chosen here in the ultralocal measure for the metric, there's an undetermined constant in front of the measure. That constant would change the measure here by some alpha associated to each mode. That product over alphas over rescaling of the measure can again be absorbed in S naught. Good. Finally, why did we get this factor of 3/2? We got this factor of 3/2 because we're missing in this product over all the modes, we're missing the free modes that correspond to the SL2R transformations of the patch of ADS2. So if here we would have had a product over all n, we would have in principle obtained no beta dependence. That beta dependence is captured precisely because there are free generators of SL2R that we haven't integrated over because they're not physical modes of the metric. Good. And somewhat miraculously, because the integration space is symplectic, there's an argument that the integral over T of u is actually one loop exact. And I could go into more detail about that if you guys want after the course. But for now, let's take it as is. Yeah?
So you calculate the quantum correctness to the saddle. Is there any other saddle? Because when people calculate the Schwinger effect, I remember that there are a lot of saddles, 1 instanton, 2 instanton, and so on.
Yeah. So in principle, if you have other saddles in the bulk, you should sum over them and include quantum fluctuations around each of them. Since you brought up the Schwinger effect, we actually computed what happens when these black holes pair produce particles in their near horizon region. And that requires exactly including an infinite set of Euclidean instanton and computing the quantum fluctuations around them. And you could show that the result is largely unchanged.
Yeah, but here, why did you not consider other saddles?
So other saddles are typically, if you consider other saddles of the metric, they're suppressed in 1 over g. So here we're only considering perturbative corrections around the saddle rather than non-perturbative corrections that are suppressed in 1 over g. So if you are interested in a regime where the temperature is perturbatively small, where T over M breakdown is order 1. I say perturbatively small, it's because M breakdown scales with Q, the scale that controls the perturbation theory. T scales with Q to the -3 in the regime that we're interested in. If you're interested in this regime, you in principle only need to care about perturbative corrections around your saddle.
I see, thank you.
Hi, Luca.
Yeah.
Following that question, so one can in principle also consider the winding modes which has a winding number not larger than 1 on the Euclidean disk. But you're saying that these are also suppressed.
Yeah, so there's 2 separate questions. Number 1 is, should we integrate over the other windings? The problem with that is that we can't actually glue this part of the space-time in which the boundary winds twice to the rest of the asymptotic part of the space-time. That's one physical reason not to include the winding modes. Sorry, further windings. So the windings come because technically you're right that here, when we solved the equations of motion for the Schwarzian, we could have put an integer n here. So this just implies that the types of spacetimes that we're looking at have the boundary of ADS2 winding multiple times around the patch. Yeah, so one reason not to include them is because we can't actually glue them to the far away region. The second reason not to include them is that it turns out that they're unstable saddles. If you do the expansion here, I think there's this one, the quadratic expansion looks different. And I think, I might be forgetting off the top of my head, but I think this number, -1, is replaced by minus the winding number squared. So for instance, if you have winding 2, the mode that has n equal to 2 will have 0 weight. And if you go to even higher winding, modes will start having negative weight. And then you have to decide whether or not this saddle gets picked up by your integration contour. Great. So let's see what effect this one-loop determinant has. So let's write the free energy in order to obtain all the other thermodynamic quantities from this. The free energy is just S0, which is pi q squared plus 2 pi squared over beta m breakdown minus beta m0 plus 3/2 log of t over m breakdown. Now, in principle, you might be concerned about other, I mentioned that in this effective field theory that we wrote down, we only kept track of this over this mode, the modes of the dilaton and of the metric. In principle, you could keep track of other massless modes that appear in the theory. If you do a quadratic expansion of those modes, what you'll find is that they have fluctuations that instead of scaling with beta, scale with q, the charge of the black hole, or the size of ADS2 or S2. So that implies that the other modes contribute factors of log q to the free energy instead of factors of beta. And to be precise, people had actually computed what the coefficient of this log q is. It has a coefficient c log over 2, where c log was computed to be minus 180 times 964 plus ns plus 62 nv plus 11 nf. So ns, nv, and nf are the number of massless scalars, vectors, and fermions in your theory. And this factor of 964 over 180 come from other fluctuations of the graviton itself. And these numbers were computed in a series of works by Sen. And this was just by taking the near horizon region of these black holes and computing the one-loop determinant of all these modes, all the other modes, except for the Schwarzschild modes, which were somehow missed for a long time. And in principle, there are subleading corrections in G Newton. And those subleading corrections contribute further factors that are suppressed in Q. And one can actually give a general argument that there is no enhancement in temperature in these perturbative corrections. So if we're interested in the limit of small temperatures, the only things that we have to look at are these terms. Oh, higher corrections in G Newton, right? Here, the scale of the dimensionless scale is set by the radius of ADS2 or the radius of S2 over L Planck. That's exactly Q. Great. So as you can see, this factor can become very important as T becomes smaller and smaller. In principle, it can dominate over this factor. This one is the semi-classical correction to the free energy. And this is the quantum gravity correction to the free energy. And as t goes to 0, this logarithm becomes more and more negative and can overwhelm this term.
So in general, is this because of one loop exact we're allowed to do this?
Yes, yes, yes. In principle, if this was not one loop exact, this would only be trustworthy, I don't know, in the regime where you could neglect corrections that are suppressed in T over M breakdown. But because it's one loop exact, we have control over all T over M breakdown corrections up to arbitrarily small perturbative temperatures.
Slightly confused with this. When T by M breakdown is much greater than 1, somehow these effects should be suppressed.
They are suppressed, yeah. So this term is the log of T over M breakdown, and it's much smaller than this term. So this is the same as T over M breakdown. Right? So when T over M breakdown is a large number, we're comparing this linear number to the logarithm of this number. It's very tiny. Now when we take this result to 0, the function x minus x plus log x is dominated by log x. Yeah?
Can you say one more time how you got the measure through like a Jacobian factor?
The measure here.
Yeah.
Yeah, so right. So in principle, yeah, you start with the measure in terms of the metric. And then we've explicitly written the metric as the ADS2 cross S2 metric plus these fluctuations that depend on tau of u. And you could plug in those explicit fluctuations of the metric in the delta G there and there. And you can compute the Pfaffian of this is like a symplectic measure. You can compute the Pfaffian of that symplectic measure, and you get this result. It's a bit subtle. There is some factors of Q that I didn't keep track of in this measure that end up propagating into this factor of C log that appears here. But this factor of C, so there's some factor of Q that I didn't actually write here, but this factor C log keeps track of the powers of Q that I neglected in the measure over there, right? Because the scale of ADS2 and S2 is Q, so the metric explicitly depends on Q, so when you plug that in to compute the measure over metrics, you'll have some explicit Q dependence. Great. So let's redo the computations that we did in lecture 1 for the thermodynamic properties of this black hole. So first, the mass, that's minus d beta log z. Let's plot it. Before we plot it, let's compute it. It's just m naught, which is q, plus the term that came from here, that we computed on day 1, that is 2 pi squared over t squared divided by m breakdown. This was the quadratic problematic piece that appeared in the paradox of Preskill and collaborators, plus the contribution that now comes from this quantum correction that simply gives a factor of free half times t, right? You just take d beta log of beta. Great. So what's the effect of this free half times t close to extremality? Well, before, the problem that we had is that the energy above extremality as a function of the temperature was below the average energy of a single Hawking quantum. And the classical energy above extremality was below that energy. Now, because of this factor of free half times t, this curve gets lifted, and the corrected average energy above extremality that these black holes have in the canonical ensemble now is always above the average energy of a single Hawking quantum. So this was average E Hawking. This was semi-classical. and this is with quantum corrections. And notice that at large T, this term dominates. So even though it's not apparent, these two curves kind of merge at large enough temperatures. So this basically addresses puzzle 1, right? We now never have the energy of a single Hawking quantum is never sufficient to actually take the black hole below extremality. I should say that we've actually addressed this puzzle a bit more rigorously by recomputing the spectrum of Hawking radiation when including these quantum corrections. And you indeed find that the statement that I just made is true, that the black hole always remains above extremality, but the spectrum of Hawking radiation is actually drastically modified because of these quantum corrections. It's no longer anywhere close to being thermal. Great. Let's look at the entropy as a function of the temperature. The entropy was 1 minus beta d beta log C. S naught, it's the thing that we wrote in lecture 1. But now, the quantum correction that I wrote over there to the free energy corrects the entropy by a factor, also by a factor of 3/2 log T over M breakdown. So now, if before the entropy went to a constant as the temperature goes to 0, now the temperature actually becomes smaller and smaller. What color did I use for the quantum corrected result? Blue. Maybe I'll keep the color scheme. So this is red. It's the semi-classical result. If you just keep the saddle point approximation, and this blue is the quantum result, and both this plot, in this plot, and in the plot on the right, quantum corrections become important when T is of order M breakdown. Maybe to relate to a question that people asked earlier, someone asked, why didn't you keep other non-perturbative effects, or when should you keep other non-perturbative effects? You see that this plot of S of T as a function of T actually has a small problem. The entropy indeed gets smaller and goes to 0, but it actually doesn't go to 0 as T goes to 0. Rather, it goes to minus infinity. And it goes to minus infinity. It becomes negative at a scale that is non-perturbatively small in the entropy of the black hole at e to the minus 2s naught over 3. So this is telling us that when we're starting to probe non-perturbatively small temperatures, this perturbative approximation that we've just done is no longer good. In principle, now you should keep other saddles in the path integral. You might be worried about saddles that at finite beta are suppressed in 1 over g Newton. Those saddles can become enhanced when I probe such small temperatures. And in fact, in toy models, people manage to show that the entropy stays positive when you include these non-perturbative effects into account, and eventually goes to 0 as T goes to 0. But in any case, this is telling us that perturbatively the entropy is much smaller than we expect.
Luca,
Yeah.
this diagram, it seems like at higher temperatures we are reaching the semi-classical. Oh, that's what we expect. Sorry.
Yeah. So high temperatures, semi-classical, low temperatures, quantum corrected. You could also see this by looking at the Laplace transform of this entropy. So you can look at the density of states that goes like e to the s of e. And what you find is that before rho of E behaved like e to the some number times square root of E at high energies. At small energies, it went to a constant. But now from this plot, it's clear that the density of states, including quantum correction, starts deviating as the temperature, as the energy reached the breakdown scale. And if you take the Laplace transform, one finds that the density of states goes to 0. And behaves as the square root of E over M breakdown as one approaches extremality. So instead of behaving like an exponential, it behaves like the square root. Yeah.
Could you explain quickly one more time the resolution on the left for that related to
Here? Yeah. So the idea is, and this is an idea that I wanted to emphasize more in my lectures, but unfortunately I didn't have time. It's related to puzzle number 4, which is that in the gravitational path integral, oftentimes when you scale a parameter with e to the 1 over g Newton, non-perturbative effects can become important. And this is indeed what happens when you scale the temperature, or beta, with e to the plus g Newton, or e to the s naught. In this case, it's e to the 2s naught over 3. That turns out to be the relevant scale. So what happens is that there's another saddle of the path integral that kicks in, at least, and we don't know what actually happens in a theory like Einstein-Maxwell theory, but we actually understand this very well in just JT gravity. There's another saddle that kicks in at this temperature scale and causes the entropy to actually, corrects the entropy by a very large amount, making it go to 0 rather than minus infinity as t goes to 0. It's actually quite complicated. It was only worked out in the past year or so. It's more like a resummation over the entire genus expansion that is relevant in this non-perturbatively small regime. Yeah?
A little question. What happens, like, what's the same, does the loop curve break down in the right figure as well because of non-perturbative effects?
In this figure?
Yes. Do I have a similar thing as there?
Yes. So here, importantly, and this relates to the set of puzzles that I don't have the time to talk about, we get a smooth density of states. So rho of E, I'll just write explicitly what it is. It's sinh, it's e to the s naught, sinh of 2 pi square root of 2e over m breakdown. Sorry for the ugly writing. I hope you understand. If not, I'll repeat it. So the important thing is that it's a continuous function, right? And that's because we're Laplace transforming that smooth function over there. It's not a sum of delta functions, as we might expect from a discrete quantum system. And the point is that if we focus on sufficiently small temperatures, we could isolate a regime of energies where the integral over the density of states can be smaller than 1. And in that regime, you might have a negative entropy. So that's what this curve going negative represents. But in reality, non-perturbative corrections are sensitive to the discreteness of rho of E, and that's how they could save the day. Good. So in what regime is all this valid? When should I trust this plot? So as I said, we should trust it only in a perturbative regime, which means that we should take t to be much larger than e to the minus any number times s naught. In principle, this plot indicates that we should trust it when the temperature is much larger than e to the minus 2 s naught over 3. But the safer assumption is to say that we trust it only in perturbative regimes. So this is the low end of the temperature. On the high end, we have taken the near extremal limit. And that near extremal limit requires the temperature to be much smaller than the inverse charge. So this is the regime in which we should trust this effective field theory. Now,
What's been changed is the fact that we used Isaac already to put on the parameters.
what do you mean?
Like higher derivative corrections to the original action.
Well, yeah, good. If you consider higher derivative corrections to your original action, you will have indeed higher derivative corrections here. But one can show that those higher derivative corrections don't affect the temperature dependence of the free energy. So, for instance, they would slightly change your boundary. Your effective field theory would still look very similar to what I wrote down before. It would slightly change the boundary conditions that we put at the boundary of ADS2. Phi b would be alpha prime corrected, and S naught would be alpha prime corrected. The extremality bound would be alpha prime corrected, but this log T is universal. So that's why I didn't even mention alpha prime corrections. So here we started with a black hole in flat space, right? Reinstein-Nordstrom black hole in flat space. But as long as the near horizon geometry looks like ADS2 times something times some compact manifold, this analysis is roughly valid. You would change what the scales L2 and ML2, S naught, M naught, and M breakdown are. But the form of the density of states close to extremality is universal. So for instance, the analysis applies to black holes in ADS. And I'll talk more about black holes in ADS free in a few minutes. But let me just say that this implies, if it applies to black holes in ADS, in cases where black holes in ADS are stable close to extremality, then this density of states gives an approximate density of states for the CFT dual in a sector of large charge. So just to relate this to a lecture last week, Zohar told you about an effective field theory for large charge in simpler models like the O2 model. In holographic theories where these black holes are stable, you might expect that the Schwarzian is a boundary EFT. For CFTs at large charge density. And it would be very nice if one could derive this boundary EFT in higher dimensions. I don't know how to do that. In a moment, I'll tell you how to derive it in two-dimensional CFTs from modular invariance. Another point is that I mentioned earlier, but let me reemphasize, is that one can not only compute corrections to thermodynamic quantities like the partition function, one can also compute corrections to other observables. So for instance, one thing that gets corrected are correlation functions of simple operators. Both, if you just take a free field in flat space and compute some correlation functions of a free field, let's say, that probes this ADS2 cross S2 region, or if you just compute a correlation function on the boundary in the context of ADS-CFT, they both get corrected if you go at small temperatures and sectors of fixed charge. And for instance, one consequence of this correction to the correlation functions is that the spectrum of Hawking radiation gets modified. You could obtain the spectrum of Hawking radiation by studying the two-point function of the field whose Hawking radiation you want to study. And all these things put together, partially at least, resolve puzzles 1 through 3. Great. Now, this was one derivation of these quantum corrections that proved very important close to extremality. There was another derivation that I was thinking about covering, but unfortunately I don't have time, in which one just starts from this action. It's a much more pedestrian approach. You could start from this Einstein-Maxwell action, take the near extremal metric and the field profile for all other fields in the theory, and literally just brute force, quadratically expand this action around your saddle point, and evaluate the one-loop determinant of all the fields. And you'll observe exactly what I mentioned previously. There will be a set of fields whose eigenvalues, whose fluctuations have eigenvalues that scale with the temperature. These will be precisely the fluctuations of the metric that correspond to these Schwarzian fluctuations. And then there will be a set of fields whose eigenvalues, you want to compute the determinant of all the differential operators associated to the quadratic expansion of each field. You can evaluate the eigenvalues of that differential operator. Some differential operators will have eigenvalues that scale with t, and others will have eigenvalues that scale with q.
I have a question on that.
Yeah.
You just mentioned that the three half coefficients come from the three modes that you don't integrate. I'm wondering if you can reproduce that exact coefficient from reading from your result of the determinant.
Yes, you can.
So there's
Yes.
like
You find an infinite set of modes that scale with the temperature, and there's a residual set of free modes that have eigenvalue that's parametrically smaller than the temperature. It's basically 0 if you take the extremal in the extremal limit, and those are the free SL2R modes.
Does that mean there's underlying like SL2 symmetry even if you just look at the four-dimensional action, but around the just curious, how can you?
I'm not sure, but yeah, I'm not sure. I wouldn't make that such a strong statement. But yes, there is an SL2R symmetry in the near horizon region. It's not a symmetry of the entire space-time, which I think is what you're asking. But people did compute the eigenvalues of this differential operator on the entire space-time and indeed reproduce these free 0 eigenvalues. Yeah.
This other approach, we don't have to restrict to the S wave. Somehow can be.
Yeah. So here, yeah, maybe let me make a comment about that too. So actually, these powers of Q came both from the S wave and the higher angular momentum modes of fields that were massless in higher dimensions. And that you can see because the mass of a field reduced on S2 scales with the inverse size of S2. And that's exactly Q inverse. So these, the fields plus all higher modes, all higher angular momentum modes, are exactly responsible for these, the coefficient of the log Q in the free energy, or the powers of Q in the partition function. Great. Any other questions? Yeah.
Would you get the similar log Q factor if you were considering the usual Iliesiu derivation with the decoupling limit and the black ring? Does this sort of come from some lack of decoupling? Maybe I can ask this.
No, I think it's a great question. I think you do. I guess you can. So the question was, do you get these similar factors of log Q in the in ADS-CFT, right? Yeah, I think in some cases you do get one-loop corrections that scale with the central charge. Yeah, I need to think a little bit about it, but I think you do. So for instance, for black holes, you have log n corrections to their entropy. And those are similar to these factors of log q.
So you said the C is like a central charge?
No.
Oh, okay.
No. That's not what I meant. I meant that Q is the thing that's more similar to the central charge. Right? In fact, like in ADS-CFT and the derivation of ADS-CFT, we relate the central charge to the charge of the branes, right? Great. So now, since you might not believe all these derivations, let's provide yet another derivation that in the context of ADS-CFT is purely from the boundary side. I think this derivation is very nice because it also teaches us how to correct some computations that we've done in the past. So deriving these corrections, quantum gravity corrections, in ADS-free CFT2. So in ADS-free, in any theory in ADS-free, we could study black holes close to extremality that have large angular momentum. So in ADS-free, there are BTZ black holes. And these BTZ black holes can rotate. And they similar to how Reinstein-Nordstrom black holes have an extremal limit in higher dimensions, BTZ black holes have an extremal limit in which the extremal energy of the black hole goes like the angular momentum minus 112. Or maybe at large angular momentum, classically you just get it that it goes like the angular momentum itself.
Any reason when we are taking rotation, in that case we have charge. Like BTZ can also be charged. Get extremal like that.
Yeah, I guess the argument in ADS-free is sufficiently universal that we can talk about black holes in theories that don't necessarily have other gauge fields. We could even talk about this argument in the context of pure gravity theories. Good. So our goal, just like before, is to compute the partition function of the black hole, which according to ADS-CFT is related to the partition function of the CFT, which we can compute as fixed beta and fixed angular velocity theta. So here theta, we could think about it as the other direction on the torus. So z of beta and theta is trace e to the minus beta h in the CFT minus I theta j. So theta is like beta omega. Great. So it will be convenient to express things in terms of the modular parameter of the torus, tau, on which we put the theory, which is theta plus I beta over 2 pi. But since we'll be interested in the regime that will be relevant to isolate the contribution of these rotating black holes will be imaginary theta and real beta, real temperatures. It will be more convenient to work with an inverse left and an inverse right temperature that we relate to tau and tau bar in the following way. Tau is I beta left over 2 pi, and tau bar, that is theta minus I beta over 2 pi. This is minus I beta right over 2 pi. Great. Here, the Hamiltonian is related, the Hamiltonian and angular momentum is related to the Virasoro generators. H is L plus L naught bar minus C over 12, and J is L naught bar minus L naught. Now, in 2D CFT, there is a very powerful technique called modular invariance, which relates the partition function at low temperatures to the partition function at high temperatures. Now, if I just look at non-rotating BTZ, the states at low temperature are just the vacuum state is dominated by the vacuum. The states, the partition function at high temperatures is dominated by black hole states. And this is the derivation that Cardy provided to compute the density of states of black holes at high energies. So more generally, if we evaluate Z as a function of tau and tau bar, modular invariance tells us that Z is invariant under gamma tau and gamma tau bar, where gamma is an SL2Z transformation that acts on tau and tau bar as A tau plus B over C tau plus D, where A, B, C, D is a PSL2Z matrix. Right? So let's look the most standard transformation, the one that maps low temperature to high temperatures, is the one in which we send tau to -1 over tau. And this corresponds to A, B, C, D equals 0, 1, -1, 0. It is known as an S transform. Together with tau going to tau plus 1, that's called the T transform. These two transformations can generate all of SL2Z. Great. So let's apply this modular transform to the partition function, but not only when we keep a beta, but also when we keep theta. Because by keeping theta, instead of looking at BTZ black hole, we can isolate rotating BTZ black holes. So writing the partition function in terms of beta left and beta right, a modular transform changes beta left and beta right by sending it to 2 pi squared over beta left, 2 pi squared over beta right. On the other hand, we can always rewrite a partition function as a sum over states. So let's rewrite this partition function as a sum over states. The sum over states in a 2D CFT can be more conveniently rewritten in terms of a sum over Virasoro characters. The sum over states in a partition function arranges itself in Virasoro characters, and we get a contribution from the Virasoro character associated to the identity and all of its descendants, evaluated on 2 pi I over beta left, 1 evaluated on 2 pi over beta right, plus a sum over Virasoro primaries, two pi I over beta left, chi h bar, 2 pi I over beta right. Now, we're interested in a regime where in here, on the left-hand side, the partition function would be dominating by these rotating black holes. We want dominance from rotating BTZ. And depending on that, we can see which one of these states dominate on the right. So if we want extremal rotating BTZ to be close to dominating, do you guys prefer if I write there, or yeah, maybe I'll write here. If you want black holes, near extremal BTZ to dominate, we have to go to very, very low temperatures. And taking that, so implies that we should take beta large, beta left to be very large. Now, if we work in a holographic CFTs, we're working in a theory that has large central charge. And to isolate the black hole states close to extremality, we should take beta left of order C. Now, in order for black holes to actually dominate this ensemble instead of vacuum states or descendants of the vacuum, it turns out that we need to take beta right to be sufficiently small. This makes theta be very large, if you look at the definition of beta left and beta right in terms of beta and theta. So taking beta left times beta right to be smaller than 2 pi squared ends up being the regime, choosing these three parameters. We are actually in a regime where on the left-hand side, these near extremal rotating BTZ black holes dominate. What happens on the right-hand side? For that, we just have to take the limit of all these characters as beta left is very large and beta right is very small. And it turns out that it's actually pretty easy to do. And that is almost what Cardy did back in the day, with a small difference. Namely, in this regime where we take beta left to be very large, expanding the Virasoro character, I wrote an explicit formula for what the Virasoro characters are in these notes. Feel free to look afterwards. You can plug it in Mathematica, and take beta very large in this equation, do a series expansion. You'll find that it grows exponentially with beta left over 24, plus a factor that depends on the central charge over 24, 2 pi squared over beta left. So this should almost remind you of the free energy that we got in the semi-classical limit for a near extremal black hole. But in the limit when beta left is large, there's another piece of the Virasoro character that ends up being important that comes from summing not only over the vacuum, but also over all its Virasoro descendants. And that piece goes precisely like 2 pi over beta left to the power 3 halves. Now, you could similarly take the very large temperature limit for the right movers, and this gives you a factor that goes like e to the c over 24, 2 pi squared over beta right. So putting these two results together, one finds that the partition function at fixed beta left and beta right is just the product of the two. So I won't write the product, but importantly, you could take the Laplace transform of this product of two functions in terms of theta and beta to derive what the density of states in a sector of fixed charge is. So z of beta and j is the integral over d theta e to di theta j z of beta left, beta right. And then we can write z of beta and j as an integral over dE from E naught to infinity, rho of j of e to the minus beta e. What one finds after doing this Fourier transform and an inverse Laplace transform to obtain this rho j of e is exactly the density of states that we wrote before. It's sinh of 2 pi square root of e minus e naught over m breakdown times e to the s naught, where, let me write what all these parameters are. As a function of CFT quantities, m breakdown turns out to be perturbatively suppressed in the central charge, goes like 24 over C. E naught is J minus 112. And S naught, the entropy of these extremal black holes, goes like 2 pi square root of Cj over 6. So you see that when I'm at very large energies above extremality, what you recover is just Cardy's standard formula for the density of states, which predicts that the density of states grows exponentially in the square root of the energy. And that's exactly what you get when you expand this singe. But now, at very small energies, as we approach the extremal bound in a sector of fixed J, we see that the density of states predicted by Cardy goes wrong. It's no longer exponential, it becomes this singe, which close to the edge becomes like a square root of E minus E naught. And this is because in Cardy's formula, one now also has to take into account this factor in the large beta L expansion of the vacuum Virasoro character. So this is basically a refinement of Cardy's formula that precisely reproduces the Schwarzian density of states.
Can you remind me, what happens to the other, to the sums over other parameters?
Good. So in this limit, one can show that the contribution of any individual primary is exponentially suppressed in h bar, in the value of h bar of that primary. It's exponentially suppressed in C, so the contribution of all these primaries is exponentially suppressed in C times h bar, the gap in h bar up to the first Virasoro primary. Assuming that gap is not parametrically small in 1 over C, you get that the contribution of these states is suppressed. Now, it's a bit more subtle than that. People have wondered whether it's the contribution, the sum of all these states can end up overwhelming this exponential suppression. The answer to that question turns out to be no, but the proof of that is quite complicated, even in the standard case of Cardy's formula. Great. So let me make some final remarks, which is, maybe I can answer, okay, fine, go ahead. Yeah, so roughly speaking, we want black holes to have large angular momentum, and we want the energy to be close to the angular momentum. And that roughly implies that we should take beta and theta. We should take actually theta to be purely imaginary and beta to be real, and take both of their absolute values to be large. And this exact inequality comes from imposing that what dominates on the left-hand side are actual black holes instead of descendants of the vacuum on the left. Good. So final comments. Now, we derived this density of states for black holes in ADS and for black holes in flat space. But this density of states has the feature that the density of states seems to vanish at extremality. Famously, one of the most important results in string theory counts the number of black hole microstates of extremal black holes. This is the result of Strominger and Waffe that provided an explicit count for the number of BPS states in string theory constructions of black holes. And they don't find that the extremal entropy vanishes. Rather, they find that the entropy indeed grows like the area over 4G Newton. So somehow, all these results should be wrong in the extremal case. In the supersymmetric case. So all results are modified in supergravity when looking at near BPS black holes. And this is because in supergravity, roughly speaking, the Schwarzian modes, which are a set of fluctuations of the metric, when you expand around the background that preserves supersymmetry, those modes have superpartners. And those superpartners could have as large quantum fluctuations as the Schwarzian modes themselves. So the one-loop corrections, all the one-loop corrections that we've considered have to be modified. So for instance, if we discuss black holes in flat space in n equal to 2 supergravity in 4D, similar theory of supergravity to what Liam discussed. When you consider these BPS black holes, they're near horizon isometry instead of being SL2R is given by a supergroup for which SL2R is a part of the bosonic subgroup. It's instead PSU 1,1/2, just as an example. And we've just established that the Schwarzian mode could be viewed as a Goldstone mode for the breaking of SL2R due to the profile of the dilaton in this background, right? That explicitly broke the SL2R isometry. Similarly, in the supersymmetric cases, we have a more complicated supersymmetric theory, an n equal 4 version of the Schwarzian. It can be viewed as a set of Goldstone and Goldstino modes for the breaking of this isometry. And if you quantize this theory, it turns out that the theory is again one loop exact, and one can integrate over all the modes of the metric and all the graviton modes that are light. And one can again obtain the density of states in sectors of fixed charge. So for instance, rho of V when j is equal to 0 turns out to have an exact delta function extremality whose coefficient goes like e to the s naught, e to the area over 4g Newton, where the area is the area of the extremal solution, that has a gap which goes like e breakdown over 8, m breakdown over 8. So for if you just take a black hole that has a single charge in n equal to supergravity, it would be like 1 over 8 q cubed. And afterwards, it has a continuous density of states that at large energies has a behavior that's similar to the non-supersymmetric case. But the important thing is that close to extremality, we actually see that the density of states is so much modified that quantum corrections cause there to be an entire gap in the spectrum. And you could actually show that if you perturbatively expand around other saddles to the path integral, this gap in the spectrum actually persists. So this is this effect can be seen using the first derivation of these quantum effects, writing an effective field theory in ADS2 cross S2 around these black hole backgrounds. You could also see it in the second derivation by explicitly expanding the supergravity action to quadratic order. And finally, just to relate this back to Strominger and Waffe, Strominger and Waffe applied Cardy's formula to get an estimate for their count. But we just saw that Cardy's formula is very subtle in the extremal limit. Namely, to correctly use Cardy's formula in the extremal limit, you really need to correctly do the expansion of the vacuum Virasoro characters and consider the appropriate beta left and beta right. And it turns out that if you do that, instead of doing applying this method for the vacuum Virasoro character, if you use the vacuum n equal 4 super Virasoro characters, and go through this expansion, do a modular transform and isolate the density of states of black holes that almost saturate the BPS bound, you again on the nose get this density of states that has a large degeneracy at extremality followed by a finite energy gap. So this is just to say that the correct version of Strominger and Waffe that counts BPS states should really be refined a little bit to accommodate this limit of very low temperatures. So it's nice to see that it's nice to see that perturbatively you get a gap in the spectrum and the large degeneracy at extremality. This is kind of a first signature that from the gravitational path integral you can compute a discrete, you can see a discrete Hilbert space. You can do much more. Turns out that in special cases you could even compute the integer degeneracy of BPS states. And using other kinds of non-perturbative corrections, you can probe different signatures of discreteness in this regime. And the signature of discreteness have to do with the black hole information paradox, which Netta will talk more about next week. All right, thank you.
Since we're a bit over, let's postpone any further questions to afterwards. Luca will be around next week, correct?
Yes,
and
correct.
He's also giving the public lecture next week, which we'll talk more about next week. So you'll have more time to talk to him. But this is his last regular TASI lecture, so let's thank him again.